All right, in this video, we are going to look at the steps of an action potential, looking at key vocab terms like depolarization and repolarization, and what's happening with the ion gradients that we might call graded potential. So we'll jump in and take a look at this. So my students will probably recognize this graph because we've used it quite a bit. There are three main checkpoints along the graph that we're going to look at. So I'll draw these as dotted lines and explain what each of them are. This graph is measuring millivolts. That's what the y-axis is. And then this is measuring time in milliseconds. So really quick events happening very rapidly. And it's measuring the voltage of the cell membrane of a neuron. And neurons work a lot like computers or computer programs, where different values need to be met in order for a program to run. The way that I think about it and the way I talk to my students about it was if you've noticed a Ring doorbell camera that will detect movement. Essentially what that computer program is doing is analyzing each frame of an image, and anytime the image changes from what it remembered before and meets a certain threshold, so a certain amount of change in a certain amount of time, it's going to detect it as movement and cause the computer program inside that doorbell camera to start recording the video or send a notification. And so it works a lot the same for neurons. In order for them to want to send that message along to the next neuron, so pass it from the axon terminal of one neuron to the dendrite of another neuron, we need to meet a certain voltage. So the resting potential of the cell membrane is at about negative 70 millivolts. The next checkpoint is happening at around negative 60 millivolts. And then up here at the peak, when it gets passed on or when some action is taken, that's happening at around positive 35 millivolts. And this might be different depending on what graph you look at, but it'll be close to these numbers. The idea is the same. So in an action potential, there are 5 main events taking place. The first one happens from resting potential up to this 60 millivolt line. And so we might call this step number 1. Step number 1 is the threshold stimulus. And the threshold stimulus is essentially just the minimum amount of voltage needed for that neuron to consider the message important. And so we'll just write that down as a definition. So this is the minimum stimulus needed to trigger an action potential. Okay, so that's step number 1, threshold stimulus. We meet that, the neuron's going to consider that an important enough message to send on, or at least to consider sending that message on. What happens next in the next phase of this graph is it's going to spike rapidly. The voltage is going to spike really, really quickly. And this is what we would call step number 2. Step number 2 for us is going to be the event called depolarization. Okay, so depolarization, what's happening here is we'll imagine that this is the cell membrane. So the cell membrane, I'm going to abbreviate, but this is the cell membrane. And on the outside of the cell, the environment is generally pretty positive. The inside of the cell is generally rather negative. And that's due to different ions. If you've taken chemistry, you might understand that an ion is just an atom that has a charge. And so we have cations and anions. If you need more description on that, I've got a video and I'll try to link it in the description of this one that you can check out later. But in the instance of what we're talking about in this video, the ions we're working with during depolarization are sodium, Na+. And what happens, what causes this big, huge increase is that when the threshold stimulus is met, sodium gates are going to open in the cell membrane, and all of the sodium is going to rush into the cell, making the cell get really, really, really positive until it reaches its peak. Once it has reached the peak, this is, we'll just call this step number 4, step number 3, and this is the action potential. And the action potential is when that message is actually sent on to the neighboring dendrite of another neuron, to the target tissue of whatever, like a muscle or a gland. The example that I used in class was, let's imagine that you get a text message, a picture of a toilet. Let's say a toilet in a boys' bathroom at a high school. It's just a regular toilet. What's the likelihood that you would send that message to a friend? Just based on the picture alone? Probably pretty low. So that would be kind of like, maybe we get to this, threshold stimulus. We recognize something has happened, but it's not enough really to trigger this to go all the way up. So we kind of got up here, didn't quite reach it, and then it would just fall back down. Didn't quite hit that threshold stimulus. But once we hit the threshold stimulus and we realize that it's something that's important, we'll send it on. So the example would be, instead of just a regular toilet, if somebody sent you a picture of a toilet in a boy's bathroom with a burning pile of garbage on top. Like, if you got that photo of garbage on fire on a toilet, that's pretty rare. You don't see that every day. And that's probably an image that you would forward onto your friends or other people that you know, because it's unique and different and interesting. And so that's what happens when we hit this threshold potential. It triggers this cascading effect where all of these sodium ions are going to rush in. And they want to rush in because of diffusion. Diffusion tells us that molecules want to move from an area of high concentration to an area of low concentration. And that's the state. So it's positive outside of the cell. We have a high concentration of sodium ions. As soon as these gates open, the only thing that fits through is sodium, and it rushes from high to low. That's what we would call a graded potential. And it starts to make the whole situation generally way more positive. Okay, step number 4. After this action potential is reached, another set of gates are going to open, and it's going to cause a graph kind of like this. It's going to drop really rapidly. So this would be step number 4. Step number 4 is the opposite of depolarization, kind of the opposite. We call it repolarization. Okay, so repolarization, what's happening now, so here's the cell membrane. What's happening now is the outside of the cell has become a little more negative now, and the inside of the cell has become generally more positive. That's what we're seeing up here. The cell is generally more positive than it was before. What this action potential does is it triggers another set of gates to open on the inside of the cell membrane. So these gates will open, and instead of the sodium rushing out, remember they went from an area of high concentration to an area of low concentration, which means that's where they want to stay. What we've actually had been building up inside of the cell also is a potassium ion. So potassium ions are inside of the cell. During repolarization, after an action potential, these voltage regulated gates are going to open and all of the potassium is going to rush out. And it does it so quickly, and there's so much potassium that the general net charge of the membrane actually becomes negative. And you'll notice I didn't draw this on accident. It actually goes way below where we started at a resting potential. So that's step number 4. So 1 is the threshold stimulus. So we get enough stimulus to deem something important, and that triggers these voltage regulated gates to open for sodium ions. Sodium ions are going to rush into the cell, just because they're going from an area of high concentration to low concentration. That will trigger an action potential. That action potential is the nerve impulse being sent to the neighboring dendrites or the target tissue, like a muscle or a gland, to get it to do something, to get it to send that. And then it repolarizes. It triggers the opening of these voltage regulated gates for potassium. Potassium will leave because what it's done over time is it's built up a high concentration of potassium inside and a low concentration outside. So this is another example of a graded potential where we're going from high to low. But it goes so far that it goes below where the resting state of the cell membrane is. So for step number 5, we'll just go back to blue on this one. Step number 5 is where we want to get back up to our resting potential. So step number 5, what's happening to get us back to resting potential? This is where active transport comes in. So now we're linking in, we've got a little bit of chemistry, learning about ions. We're going back to biology basics, learning about diffusion and active transport. Active transport, remember, is where the cell membrane has proteins that are actively pumping molecules, or ions in this case, against their concentration gradient. So they're going from an area of low concentration to an area of high concentration. So what this looks like here is during resting potential, we'll say sodium, potassium, potassium pumps actively move ions across the membrane. And the goal is to reset the membrane. Okay, so this is like a reset. That's what it's doing. So that's basically it. So we have our graph here. So this is a graph that you'll probably see on your exam. I know my students, you definitely will see this on your exam, but these are the basic steps. So step 1, getting to this threshold stimulus. Threshold stimulus is going to cause all of these sodium gates to open because they're voltage regulated. That means when it gets to this certain amount, that's like your Ring doorbell camera activating because it detects movement. It's going to send a signal saying, hey, this is important. Pass it on to the next neuron. And then what this action potential does, it's another voltage regulated gate. When it gets to positive 35-ish, it's going to cause the potassium gates to open. These ones will shut, the potassium gates will open, and we have this other graded potential happening where we're going from a high concentration of potassium inside the cell to a low concentration outside, and that causes the voltage to drop, and just to drop all the way. And so then what we have to do to get back to a resting potential so that the neuron is ready to receive more signals is we'll need to actively pump, using active transport, pump sodium and potassium either inside or outside of the cell, depending on where it needs to go. So hopefully that helps. I know some of you missed class because of college day. Others of you might not even be my students, and you're welcome to this information as well. If you have questions, shoot me an email. If not, make sure you study. We got a quiz next class. You guys will be good to go. All right. See ya.